All right, guys, let's get started. All right, guys, we're gonna get started. Quiet down. So first thing, quiz. Last quiz is gonna be a week from today. Questions in terms of what to expect on it. Since what we will have covered, what we'll effectively cover is basically through this week. So it's going to be a decent amount of material on it. It's going to be sugars, it's going to be lipids, and it's going to be what we're going to talk about today, amino acids, peptides, proteins. The one thing that I'd like you guys to perhaps you could take a look at is I did put a worksheet up there. I realized somebody emailed me, I had it labeled as carbohydrates, but it was like everything but carbohydrates. If you go back to the quizzes, quiz 4 from 2014, there's some good carbohydrate questions on there that are pretty much in line with it. What I think in terms of carbohydrates that perhaps you guys should perhaps prepare for is, I'll just put this on every quiz. So everyone will get a question, and this was actually the first question on all of the other quizzes. And you can even practice just on your own by drawing them, is to basically draw a sugar sequence in a Fisher projection and convert it into an appropriate chair conformation, for example. So again, it would be a question like, so I might give you a question like this. Actually, I will give everybody a question in this vein, so just be prepared for it. I think it'll be a good opportunity to sort of just make sure that you guys are grappling and continue to work on sort of spatial orientation while sort of thinking about the sugar. So I'll give you a question like this. I'll ask you to draw in an appropriate chair conformation. So again, there's going to be multiple possible right answers. Yes? Chair, not a Hallworth. Yeah, Hayworth or whatever you call it. Yeah, no, a chair, because that's what they really look like, right? And again, there's going to be multiple possibilities, right? Because when we're talking about sugars, it's not necessarily as clear whether something's going to be one chair conformation or another chair conformation. It's not clear whether it's going to be, say, for example, axial at the anomeric position, equatorial. You'll get some mixtures of them. So just draw it into something appropriate that addresses the appropriate stereochemistry, starting from something like this. And again, that's what I did last year for sugars, and that's what I'll do this year. And again, there could be questions about lipids. And today, what I think I'll show today, I'll also have a synthesis question that everybody will get as well. So this quiz, everybody's going to know what's going to be on it. There'll be 3 questions. One will be this. One will be a synthesis question, and I'll give you guys, we'll go through kind of what I'm thinking about. It's going to be peptides, how to actually make peptides, and there's a reason why I want you guys to think about this as sort of strategy within what we call orthogonal protecting groups. So it's going to be a little bit different than perhaps what you've seen if you've been reading ahead in the book. I'm going to throw an additional protecting group at you, and I'm going to sort of try to put the emphasis on how you would synthesize molecules in sort of orthogonal protecting groups. And then, again, something else that'll just be to make sure you're keeping up with the reading. All right, so today, amino acids. Okay, so to date we've talked about 2 classes of biomolecules. Yeah. You probably could. I don't know any off the top of my head, but like in terms of, because I've gotten that question from somebody else. Isn't that what you asked me? Yeah, you too. Well, I think that may be where you're coming from. So there are classes of sugars that are sort of amino sugars, and we really haven't discussed those that much. So for a synthesis point of sort of asking you to selectively, say for example, change one of those hydroxyls to an amine, yeah, I mean, it would have to be a pretty loaded question, right? It would have to be, like, if I were to ask a question like that, it would have to be a situation where it were very loaded, where somehow I gave you the ability to make sure that it would only react with one or something like that. So certainly you know how to take alcohols and convert them to amines, right? Right? If you were going to take an alcohol to amine, you'd turn it into a halogen probably, displace it with, say, for example, an azide or the, you know, or the succinimide, right? And then just sort of either reduce or hydrolyze with hydrazine or something like that. So you guys have methods to do that. In the context of the sugar, the question would then become the selectivity. Tribelli was asking about that a little bit. Where are these? Where do they come from? And again, we're talking about biomolecules at this point, so a lot of these interconversions are likely driven by enzymes. So enzymes can do things that perhaps certainly you guys haven't learned to do, and even chemists today still struggle in terms of selectivity. We can discuss afterwards if you want to suggest some synthesis questions to do it. So if you're talking about a multi-step synthesis, yeah, we can hash out a synthesis question that way if you want. Anyway, so we've discussed sugars, we've discussed lipids. Today we're going to discuss, in the next two classes, we're going to be discussing amino acids and peptides, and then we'll sort of finish up the following week with nucleic acids, and that'll be it for sort of the sort of biomolecules, but then we'll talk a little bit about polymers, and that's going to be pretty much the end of the course. We should have a couple of reviews. So again, amino acids and peptides, the sort of basic structure of an amino acid, as many of you guys already know, right, is you're going to have something that might look like this. Again, on the one hand, you have a carboxylic acid, and the amine. I've sort of shown them in the, say, for example, neutral pH, right? Because if we think about what this structure might look like, normally, sorry, not normally, but in terms of the neutral state, what we have here, right, is a carboxylic acid and amine, right? And if you guys remember what the pK of a carboxylic acid is, right, somewhere around 5, 3 to 5, that range. So again, if you're a pH above 5, right, it's going to be deprotonating it. So at a pH of about 7.5 or so, right, it's going to be deprotonated, right? pK of an amine, and what we're talking about here is not the deprotonated version, but we're talking about the protonated versus unprotonated. What's the sort of rough pK? What's that? It's up in that range. I think triethylamine is like 12. I think the primary amines are probably in that 10 range. But the point is that it's up in that higher range. It's above 7, right? So now we're more acidic, right, at that point. And so at that point, what we have is the protonated form. And so an amino acid is often what we would call sort of zwitterionic in nature. So zwitterionic basically means a molecule that's overall neutral, but it has sort of two different charges. It's a little bit different than ilids. Ilids, they're generally next to each other. So this is a zwitterion. Again, that's just terminology. Again, in terms of the amino acids, there's many of these. And again, you guys will learn more about these. I'm not going to ask you guys to hash out the different amino acids and the names and such, but certainly it's worth it to recognize what types of groups they can be. So I had a few. Right, and so depending upon what this R group is, this is what we would call, sort of call this the side chain. And the side chains can be various. So they can be basic, right? So an example of a basic one, right, is sort of an amino side chain. So this is lysine, again, at physiological pH, it's probably not going to be neutral, right? It's probably going to be positively charged. Again, for the same reasons we outlined previously, right? And so this could be a positive, so this could be a side chain. You can sort of think about it as being basic, but really oftentimes what happens is in that side chain, it's actually positively charged. So you can think about it as being a basic residue, or you can think about the side chain being positively charged. It can also be, so this is lysine. And again, I'm not going to quiz you on the names of them, I'm just sort of showing them. They can be acidic as well, right? And so if they're acidic, this could be something like R equals that's 2 carbons in that group there. Again, this is the acid, its name is glutamic acid. Aspartic acid is another one that's like that, it's just 1 less carbon. But again, this is why it's called glutamic acid, but again, at physiological pH, right, it's going to be deprotonated. Right? So in the same way that this is sort of considered a basic residue, in actuality, in this living system, or in the biological settings, you can sort of think about it as positively charged basic residues. In the case of acidic residues, you can sort of think about these as being negatively charged. They can also be, there's a lot of different ones that are sort of non-polar, right? So certainly these are both polar. Okay? So there's lots of them that actually don't have any heteroatoms on them, they're just saturated. I have written down here, leucine. So this one's leucine. You also have different versions of that. You actually have isoleucine, for example. So there's, again, a variety that simply have grease, if you will, to take something from the lipids chapter, right? So it doesn't really have anything associated with it. And then you also have things that are aromatic as well. So an example of an aromatic one that you guys have all heard of is tryptophan. Okay, tryptophan is, draw it right. Right, so that's got an aromatic appendage. There's phenylalanine, for example, which is another one. And so again, you have this sort of array. There's certainly others as well. Things like methionine and things like cysteine and serine, which again are other groups. You can sort of find these all in your books. But the reason why I just want to show sort of 4 and put them up there. And again, if you want to sort of read through more of them, you can. But I want to sort of just make a point about these, right? Especially, you're going to be taking a course in biochemistry. Many of you likely will. You'll probably be talking about protein folding and so forth. And when you start to think about the side chains, right, of many of these different molecules, you start to recognize that there will be this sort of secondary structure associated with them, right? And what that's largely going to be dictated by is what some of these different side chains are. So say, for example, if you have a few aromatic groups somewhere near one another, they might end up coming in close proximity to one another and have, say, for example, pi-pi stacking, either facial or sort of pi-cation sense. You know, again, as we sort of learned about lipids and stuff like that, sometimes greasy molecules will like to be together, and so maybe within that peptide you'll have a whole bunch of greasy components that will be together that will sort of force it to adopt a similar point. Again, you might have groups like these in close proximity to one another, and those might form, say, for example, salt bridges, which might hold the proteins in different directions and so forth. So it's important to recognize that there's not a ton of these, but within that they obviously have a very important role, specifically in terms of the secondary structure. And we're not going to go into that secondary structure. Again, this is organic chemistry, so what we're going to just sort of focus on is the sort of small molecule component with it. But when you take your course in biochemistry, as many of you will, you know, you'll see these and you'll sort of recognize this factor associated with them. Okay? And again, you can read up all about them. Okay, so certainly amino acids make up peptides and proteins. So again, the reason why we care so much about amino acids is they are the building blocks behind really the majority of what makes us us in a way, right? Sort of learn about nucleic acids in the sense that certainly the proteins, when we think about the enzymes that have their specific function, when we think about the antibodies that are in your body, when you think of things like collagen, certainly fibrous proteins, right, your hair and stuff like that, much of what we are is made up of sort of proteins, right? And what, as many of you might already know, right, peptides and proteins are effectively just amino acids tied together, sort of nitrogen to carbon. And so what you have is we'll just say R1, R2, but what we're talking about here is a repeating unit, right, of these types of groups. So there'll be a series of amide bonds, right? So you have a carboxylic acid on one side, you have an amide on the other. We'll talk about how we can actually do this. Certainly the body does it in a different way than you do it in the lab. But as we'll talk about synthesizing peptides, what you're effectively doing in this chemistry is just making a series of amide bonds, right, between carboxylic acid and amines. And so, again, these can be hundreds, thousands of units long, and they will effectively create the sort of biomacromolecules that we have. And so what differentiates, say, for example, a peptide from a protein is simply the size that we're talking about. And so again, is there sort of cutoff where you start talking about something as a peptide versus a protein? Maybe, I don't know. But the idea is that smaller sequences, you know, things like 10, 15, we generally think about as things like peptides being smaller, 2, 3, 4 would be peptides, and once you start getting to larger ones, it's proteins. So certainly there's probably some gray area where something could be sort of a quasi-protein peptide or something, but I don't know, it doesn't really matter. But anyways, this is the general structure behind them. Now, as synthetic chemists, I thought one of the things we would probably spend time on, or as a synthetic chemist, I thought one of the things that I would spend some time on is talking about how synthetic chemists make these molecules. And I think that there's some interesting things that we can learn about this and discuss about this within synthesis. And I think it could create some nice problem solving for you guys. Again, if you're thinking about certain things that could be on quizzes or exams, I just told you that pay attention right now because a lot of things associated with this will be on the upcoming quiz. And so what I'll say is, call this synthesis of peptides. And again, if a molecule like this so if a molecule like this, right, is made up of much smaller subunits and making amides, then really the only reaction in principle, right, that we would need to learn to do this, if we could be fully selective, is just amide bond forming reactions. That's where we're going to start today. We're going to discuss how you can actually do amide bond coupling reactions in the lab. Now, we've learned ways in the past, right? If you take, say, for example, an ester, like a methyl ester, and treat it with an amine, right? Certainly you can like heat that and you can get it to couple, for example, like that. But again, it turns out that in peptide chemistry, there are things such as potential epimerizations of these bonds and so forth that people have developed a specific type of coupling reaction that tends to work pretty well from them. And the reagent, basically what we want to do, I'll put this up here and then we'll discuss the mechanism of it. Say R1. We'll keep it in neutral for that right now, just to make our lives easier. But obviously there's going to be protonation changes and stuff here, so don't freak out too much. But what you're going to do is you're going to take these two and you're going to mix them together with something called DCC. And I'll draw and show you guys what DCC is, and I'll show you the mechanism. And in the presence of a base, usually something like triethylamine, you can make that peptide bond. And it turns out, again, that this is chemistry that was sort of developed in particular for peptide coupling chemistry, but certainly works with a lot of amide bond-forming reactions. And certainly we do this chemistry in our lab, or we have. I think pretty much every synthetic chemist has run this type of reaction at some point in their lives. And so what DCC is it's a molecule called a carbodiamide. So it's basically a carbon bonded to two nitrogens through a double bond, right? And on each side it's going to have, in this case, a cyclohexyl group. But there's a lot of different carbodiamides that people have basically made. This is just sort of one of the first classical ones. And what happens in this reaction, right? If you think about, again, there's going to be different protonation states in these, but you have a base in there that can sort of certainly keep some of these things neutral and certainly deprotonate that compound there. But if you imagine the base, say for example, reacting with the carboxylic acid, right, you'll be at the carboxylate. This is perhaps a mechanism that you can consider. And this molecule here is actually fairly electrophilic. Okay? And what you can do, there's many different mechanisms. Maybe I'll just go with the direct one that I like.
Why do you need this? What if it would be like amide?
What? Just react together? No, what would happen if you mix these two? This would just deprotonate that. Right? And when we learned about amide couplings, that would have to be like a methyl ester or something like that. Right, but the issue is like I said, if you're trying to do, you may have to have harsher conditions. Right, so things may happen such as isomerizations and stuff. Yeah. So I'm just trying to simplify it. You know what I'm going to start is I'm going to start this mechanism just so that we're sort of keeping everything straightforward. So again, there's lots of different protonations that can take place here. I'm just going to show one. At least reasonable mechanism, right? And so what ends up happening, or at least you can imagine this in terms of carbon counting, is that you can imagine the DCC in this basic environment. You can imagine it deprotonating the system. That's going to make a better nucleophile on this side, and it's also going to make an electrophile on this side. So this is very analogous, at least is how I'm drawing it here. It's very analogous to, say, for example, diazomethane, right, reacting with carboxylic acid. So we're sort of doing an acid-base reaction in much the same way that we did this with diazomethane to make a better electrophile and better nucleophile. At least we could consider it this way. Okay, when this happens, now if we were going to attack this molecule, where would we attack it? At this carbon, right? Because we want to push those electrons up there. We're not going to directly attack the nitrogen. We're going to attack that carbon. And what we have done in this process is we've now actually made a very good away leaving group. Okay, so now we've effectively activated this for nucleophilic displacement by the amine, right? Because if you sort of look at this, this may start to resemble something that we've seen in the past, right? This may look kind of like an anhydride to a certain extent, right? How instead of a carbon-oxygen bond that we would normally have in a double bond oxygen that we have in, say, for example, an anhydride, now we just have the carbon double bond of nitrogen. So again, this electron could perhaps be drawn back into this pi system, right? And again, at this point, you can imagine protonating this either here or at a later step, but the general idea now is that the amine can attack making your amide bond. Right? And what's going to fall off on this side, right, is we're making an oxygen-carbon double bond. We're pushing the electrons onto the nitrogen. And so what we're making here, at least this is currently shown, is the negative charge. But again, then this can be picked up, say, for example, protonated over here or whatever. But the byproduct that we're going to generate is the urea. Now, depending upon whether you want to protonate it here to help activate more, that would be another possibility. Where that protonation takes place doesn't really matter too much. But yes.
So, it just has a bitter ion, it just has a bitter ion and it's protonated by the base. How does it get neutral?
Well, so that's what I was saying sort of early on. So that's what I was saying at the very beginning, is that like these two, right, if you mix the carboxylic acid with an amine together, right, you're going to have a bis-deprotonated system. That's what I was saying earlier. We could sort of think about the base as being somehow associated with this, perhaps keeping this as the free base, if that's your concern, is that addition in. Formally, what I like to sort of think about this overall process doing, it actually ends up being sort of net neutral if you go through and you sort of draw out all the byproducts. Because what are the byproducts here? You have, once this is protonated, right, or deprotonated, you're just getting back to that carboxylate I mentioned earlier, right? So yeah, I mean, this is the mechanism. This is a rough idea of the mechanism. The important point is that you're reacting this. You know, this is one possible way that you could sort of make the resulting, again, anhydride-esque leaving group. And again, depending upon where this is going to be deprotonated, there's perhaps a lot that's going on there. So yeah, if you're concerned about the free amine, just recognize that there is base in there as well. So anyways, that's sort of how these are made. People, one of the big things that can be sometimes challenging in this chemistry, this is just so you guys know, sort of where the state of the art, for example, what this chemistry is, right? We show you this textbook chemistry, and certainly much of it is sort of older. But the product that you ultimately end up generating here when you protonate that, does anybody know what this molecule is called? It's a urea, right? So if you have a carbon, you have a molecule that looks like this. This is a urea, U-R-E-A. Right? So you've probably heard of urea in the past. Ureas you can sort of look at, maybe, I don't know, this is, I guess you wouldn't necessarily know this unless you've worked with it, but I saw Mike up in the audience, and Mike can tell you a little bit about ureas. They can be notoriously difficult to, say, for example, purify from your compounds and things like that. So people have actually done some really nice work where they've made derivatives of these that are, say, for example, more water soluble. So they'll have a charged side chain that you can, say, for example, wash away or things like that. But again, this is the sort of general idea of how you do peptide couplings. All right, so one of the most important things, so if it were that simple, right, this would be a very easy synthesis question, right? You simply take an amide and you react it, you take an amine, you react with the carboxylic acid, and you get the compound out, right? But as you can imagine, the problem associated with that, right, is that if you have say R1, and you say, for example, want to react it with R2, and you try to do this and react with BCC, you would hope to get right, so if you were to react these two together, and you would hope to get this molecule, right, just by reacting these with BCC, would be the problem associated with that? What would be perhaps one of the many problems that you would get associated with that? I heard one person make one comment, yeah.
You get two compounds instead of just one.
Well, you'd probably get a lot more than two compounds.
They just stick around.
So at the very core, right, you can imagine getting the sort of coupled product. You could also get this dimer. You could also get this dimer, which is, I think, what was brought up. You could get the inverse of those. In addition, you can start getting longer oligomers as well, right? You could perhaps get trimers or, again, oligomers where these start to add up more and more and more and more. So in peptide coupling, one of the most important components in it, in terms of being successful and able to make these, right, is protecting groups, right? And so if what you want to do is make this bond, well, you don't want to have this free carboxylic acid, right? You want to have a protecting group over here, right? And you don't want to have this free amine, you want just that free amine, right? So over here, what you're going to have is another protecting group, right? And then, so if you wanted to say, for example, get this dipeptide, right, you would do your DCC coupling, and then whatever these protecting groups are, you would then do a deprotection.
Like, I think you use the protecting group for an amino, like the molecule itself has a side chain to amine. Like
We'll get to that. We'll get to that. One step at a time. Yeah. So the question was brought up about side chains with amines, which is partly why I'm going to show you a protecting group that's not in the book, so that we can handle that. Yes?
How do you choose one of them from one and
Yeah, so it just depends upon what you started with. And so we'll discuss this a little bit. The question of how do you synthesize these building blocks is certainly something that we'll discuss. Oh, that's what you were asking? Oh, yeah. Yeah, you can't just protect them and say, right, yeah, you make this one, you make this one. That's fine. And so there's a few protecting groups. So the book talks a little bit about protecting groups. I would ignore the book. No, simply because I think it could just listen to what I say. Because the book starts talking about certain types of deprotection conditions, and I just want to make a point here. And I'm going to show you three classes. This is what we sort of call, in order to do this is what we call sort of orthogonal protecting groups. So certainly if you have a protecting group over here, you have a protecting group over here, right, and they're the same, you could do a single deprotection, right? But what if you wanted to say, for example, just deprotect the one and then keep going, or deprotect over here and keep going, right? So this is where you need orthogonal protecting groups. Or, as what was just brought up, what if I had a side chain that I had to protect? So what I'm going to show you guys today is three different classes of protecting groups. One that you can take off under acidic conditions, one that you can take off under basic conditions, and one that you can take off under hydrogenative conditions. And what I'll show you is how these work in principle. Again, some of them can actually be deprotected under strongly acidic conditions. But again, the idea here is just to sort of get you guys to recognize that there is this orthogonality, and the three protecting groups that I show you guys are just examples of many, many, many that are available in the literature. Okay, so we'll start with acid-sensitive protecting groups, or sort of acid labile protecting groups. These are groups that we're going to put on. Well, I'll just show you one that comes off under acidic conditions. Okay, and what we'll start with is amines. So we'll start with how we put groups onto the amines, and so these will all be for amine protecting groups. We'll discuss a little bit about the carboxylic acid side as well afterwards, but just to sort of get you guys thinking about the different protecting groups, all of these will be simply for the amines, okay? So if you have, just say board space. If you have a free amine, and you can actually do this in the presence of free carboxylic acids, we'll discuss how you can do this in other cases. What we're going to put onto this compound is something called a Bach group. Okay? Okay, so this is a molecule right here called Bach anhydride. Okay, so this group in the middle is an anhydride, right? So you guys have seen anhydrides in the past. You've seen acetic anhydride. This is something called Bach anhydride. Capital B, lowercase o c, anhydride. Okay. What's going to happen, as you might imagine, is we're going to add in to one of these groups. Okay. Okay, we're going to add up into the carbonyl. It's going to kick back down. And then where's it going to go? It's going to go towards the other carbonyl. Right? You're going to have a lot of arrows going here. Okay, so we'll just start there, and then I'll show you this will break down further. Okay, so this is simply the amine reacting with this compound over here. Okay, so we're going to make this T-butyl group here. Okay. The other thing that we're going to have is an O-. Okay, so this is sort of what we have sort of left over, right? What do you think this could do? What's that? It could be protonate. That could be one option, but might something else happen much quicker? Anybody see what might happen here? Yeah, we're going to generate carbon dioxide, so it's going to do a decarboxylation, right? Everybody see that, right? And what do you think that's driven by? Obviously, the release of a gas, right? A lot of times when we have a gas that we make, the gas will go away. So that will be the gas, CO2, right? And then the T-butoxide, right? And then Chava, this is what's going to then deprotonate this group. Or was it Shibeli? One of you guys said. Whichever one of you said is going to. Aren't you generating a strong base in an acidic environment? The horror. Yes. No, I mean, it's fine. And again, you can imagine this isn't that strongly of an acidic environment, right? So it's, you know, what's the pKa of those? Like 9, 8? Well, in the amide, I guess it would be a lot more. But anyway, the point is that you can go over high energy barriers. So what's going to happen here is you're going to generate T-butanol, okay? And through the process, deprotonate this here. Okay, so that's going to be our amide. Okay, so this is how you synthesize this group. You'll sometimes see this abbreviated as a Bach. Okay, so you'll see this sometimes in literature as Bach. Sometimes you'll see it as like lowercase t Bach. Okay, basically because the B stands for T-butyl, so it's like T-butyl oxy. Okay, so with this group on, what makes this molecule, so this is the decomp pathway. Sorry, not the decomp pathway. Excuse me. This is the byproduct pathway. Okay, I'm going to erase this just to get back to the original pathway. Mine. Okay, so what's going to happen in this case is that a Bach group actually can come off very readily under acidic conditions. And one of the classic acids that does this fairly readily is trifluoroacetic acid. Okay, we've seen trifluoroacetic acid in the past, right? Trifluoroacetic acid is stronger than acetic acid, so that's one advantage to it, right? It's got a pKa value of around 0 or 1 compared to acetic acid, which is like 4 or so. That's one advantage. The other advantage of trifluoroacetic acid is that it's actually fairly volatile. So unlike acetic acid, which has a boiling point of around, like I think 110 or 120, trifluoroacetic acid has a much lower boiling point. I don't remember off the top of my head, but I think it's around 70 or so. So you can actually pump it off very readily in terms of, you know, it can evaporate fairly readily. So you can sort of use it as a solvent or a co-solvent. And it works really well. And what ends up happening... Yep. ultimately, right, is that if you protonate, say the carbonyl, you have a tert-butyl group here, right? And we know that tert-butyl cations can be relatively stable, right? And it just so happens that in this case, what can happen is you can resonate into that system. Okay. With the compound that you're generating being a T-butyl carbocation, which can oftentimes get scavenged by the solvent of trifluoroacetic acid, right? So the trifluoroacetic acid, say for example, can catch it, right? Certainly it's reversible, but since you're in a solvent, that's one of the advantages to being in a solvent that's sort of a protic solvent like this, is that can go and extract that carbocation, or say for example something else in there, or can even sometimes you can get eliminations to get that off. And then it's just as brought up as once you're at this point, you're very quickly going to do a decarboxylation, right? Because what this is, right, is it's carbon dioxide and the amine. And so through a mechanism, depending upon how you want to imagine drawing this, you can, for example, use the TFA. You say, for example, protonate this first. You want to think about it like this. Right, to generate CO2 gas, and you're free of amine. Okay? So this is a Bach protecting group. So again, I just sort of, for the sake of time, the idea here is you sort of see that can break down. You can protonate this if you want to sort of keep it neutral. Deprotonate one, have the amide, even though you might say, well, I'm not going to have an amide in the solution. It's fine. If you just have it for a little bit, it's fine. The point is that that's the general way in which case you can sort of do this. Okay, so that's acid-sensitive protecting groups. The one that's not in your book, and this is in your book, I don't know if they use TFA per se, they may say like HBr or something like that. Again, it'll hopefully become clear why I don't say HBr and don't use HBr. Part of it is that TFA is what's normally used.
What is TFA itself in terms of amino acids? What does it kick off the
Oh, and leaves CF3 minus?
Yeah.
I've never seen it happen, so I guess it must be more stable. No. Yeah, well, that's the question of, yeah, I mean, then it would be a lot more dangerous, I guess. It'd be explosive hazard, and it's not an explosive hazard, so it must not happen for reasons that, yeah, but it's a decent hypothesis, but it doesn't happen, so you're safe. Yeah. All right, so the one that's not in your book is, this one's not in your book. And it's one called an FMOC group, so this is going to be a base-sensitive group that I think complement the acid-sensitive group. In this case, what you're going to have is something called an FMOC group. This is very important protecting group. Again, I'm not going to go, it's going to be very similar in terms of how you put it on there. The group is going to be a little bit, I'll just put a chloride there. It's technically called a fluorenyl. Let me try to draw this right now. Just double check this. Yeah, so this is the fluorenyl methanol, I'm pretty sure. Mike, am I right? Right, you work with this. Do I have it drawn right? That's fine. Yeah. Okay, so this is FMOC chloride. I just want to make sure this was right. I wasn't sure if it was like the arrows were in the right place. So this is FMOC chloride. Mike works with it. I thought I had it written down, but I don't. So this is FMOC chloride. Again, you would put it on in the same way. You'll see, yeah, there is a proton here. And that's going to be part of what makes it so base sensitive. Okay? So, but it's a cyclopentene, yes. Okay? What happens in this group is, again, we're going to put on we're going to put on this group here. Now this is called an FMOC. And again, it's like fluorenomethanol and the oc part of it. So what you can sort of classify this as is NH-FMOC. Yet it's not important that you sort of know that unless you want to abbreviate it and say, for example, synthesis problem or something like that, so you don't have to keep drawing the same thing. Same as that you do like TDS or something like that. Now this is base sensitive, okay? And the base sensitive nature to this is owed to, let me make one more point about the FMOC group. One of the things that's very valuable about the FMOC group is that it's not base sensitive, but it's also not sensitive to nucleophiles, right? In part because of the big T-butyl groups. That's just another advantage that I forgot to mention. Okay, so anyway, so you see lots of parallels here. This is stable to acidic conditions, but you can take it off under basic conditions, and that's owed to the relative acidic nature of this hydrogen that's right here. You can, in essence, perform an elimination reaction. Again, if you can imagine deprotonating that hydrogen, right, you're going to have a negative charge there. And that negative charge is going to be very well resonated throughout the system. Okay? So let's just bring this up real quick. So let's discuss this really quickly. Okay, so this molecule here is two aromatic rings, right? They're not in conjugation. This is a 12, 6 electrons over here, 6 electrons over here. If now you have 2 electrons here, that's now in conjugation with the rest of the system. It's now 14 electrons. Thus, this overall system is now basically aromatic. So it's for these reasons, part of the reasons why this is now really good at being deprotonated at that point, okay? All right. So the idea here, though, now is that once you have that deprotonated, once you deprotonate that, right, you have that anionic character, now that CO2 effectively release can take place, right? Because what can happen is you can do an elimination to generate your amine. Okay? So we're going to release CO2 gas, and the product that we're going to generate is going to be this double bond. And in fact, what happens here is the base that we generally use and then we get to the, basically we get to the RNH minus, which can then pick up another proton. So I'll just say RNH2. The base that we generally use in this case is piperidine. So it's usually an amine base. The idea here is that if you take this and you treat it with piperidine, so it's an amine base, it's fairly mild. That piperidine actually ends up reacting with this afterwards and generating this amine. But again, I don't really care that much detail. The important point is base-sensitive protecting group. If you want to know a reason behind the mechanism why it's base-sensitive, you can tie it back to aromaticity, right, in terms of this 14-electron system. So that can hopefully help you remember that it's this deprotonation. Linda, yes? It's the same. It doesn't matter where we draw them. I just had it on the other side. I mean, this is, you can just rotate. This is just the resin. Yeah. It's the same. I just drew them on the inside versus the outside. So it's the same thing. It's okay. So anyway, so this is the base sensitive one. So it will be stable to TFA. It will be okay to use. What's that? Will this just fall off? These with the base deprotonates them. So the base deprotonates them, right? And then what ends up happening is the base, again, I don't want to go too much into depth here, but the base then ends up reacting with this. You can look it up. You can look up. I think I posted a, if you go on the website, I have a link to protecting group chemistry on my website. All right, so that's another protecting group, and so again, what we focused on primarily is for amines. The last one is one that the book discusses a little bit, but I'm going to sort of make an amendment to it.
What do you think of carboxylic acids?
So we'll discuss the carboxylic acids in a moment. So I'll ask you guys that question in a moment. So in the case of the amine, what we're going to do is something called a basically CBZ group. So it's basically a benzyl version of a lot of these other ones. Now, if you look in your book will basically say that HBr will deprotonate this, and that's likely true. HBr is a pretty strong acid, though. HBr will probably also chew this one up as well. The reason why I showed you TFA is that it's one that's a little bit more mild. This will survive it. This will also survive TFA. This is a group that you can take off, though, under hydrogenated conditions. And so we've seen benzyl protecting groups in the past. I think I showed you guys benzyl protecting groups. We didn't go into depth in terms of the mechanism of it, because I'm not quite sure what the mechanism of it is, but you can sort of think about it as hydrogenating that bond. But the point is that you can put them on the same. It's just the only difference in all of these is this group here. And in this case, you can take it off under, say, for example, palladium on carbon with hydrogen gas. The net result in this process is toluene as well as CO2. Toluene is a solvent you can pump off, and then again you get your NH2. And so again, what we've seen here now is we've seen three classes of protecting groups, right? We've seen acid, we've seen base, and we've seen sort of hydrogenative. And again, I understand that sometimes under acidic conditions this can come off. What I'm trying to sort of show you guys, and what I'm going to try to give you guys a problem, and there was a problem like this on the final last year, is sort of something we haven't discussed yet, and that's sort of orthogonal protecting groups. How do you know when to use the right protecting group in different positions? And I thought this would be a nice opportunity to sort of explore that. All right, so this is the amine. Somebody was asking me, well, what about carboxylic acids? Because obviously that's the other component of the group, right? That's the other component of what we may want to do. So some of this you guys may already know, right? If you have, say, for example, and sometimes the question becomes selectivity, right? How do I do this with one over the other? But we do know ways to, say, for example, protect a carboxylic acid and then deprotect it under basic conditions, right? What's one type of quote-unquote protecting groups for esters that, say, for example, we could take off under, hydrolytic conditions, right? What's a fairly labile, like we learned about saponification, right? What's a fairly quick to saponify ester? Maybe like a methyl ester. So say, for example, a methyl ester, right? If we have, say, for example, a methyl ester, yeah, exactly. Right. How might we put it on there? Yeah, so we could use acid and methanol, right? So we could use diethylene, right? So we can imagine HCl methanol, or what did I say? CH-diethylene. Okay, so you sort of get that from the carboxylic acid side. Say, for example, we wanted to, say, for example, put a benzyl ether on there, right? In that same way, we've learned about benzyl alcohols, and we've learned about what if, say, for example, we wanted to put a benzyl ether on there? How might we do that? Yeah, maybe we could use, like, maybe deprotonate this with, like, K-carb or something and treat it with benzyl bromide. That might work. In the presence of a free amine, that may be a little bit challenging, but if you could, say, for example, protect the amine first and then protect this, go back and forth, but I think that would be fine. You could also imagine acidic conditions, right? HCl and benzyl alcohol, yeah. That's exactly what Linda was saying. Yeah, yeah. So you could imagine deprotonate, and I would be fine with that, right? You could argue that maybe the carboxylate, right, is a better nucleophile in deprotonated form than maybe the neutral amine. You probably get a mixture of things, but that's fine. Certainly something like, again, in the same way that HCl methanol went on there, you can imagine HCl benzyl alcohol, for example, right? Let's just say that. Again, the point is that you guys, and then it'd be the same deprotection conditions. Right? The one that you guys probably haven't learned is the acid labile one. And I'll just sort of show you guys this. I gotta be honest, I usually buy my TBO protected esters, so I've actually never done this reaction. But at least the way that the literature says that you do it is that you take a molecule like this and you treat it with excuse me. You treat it with this butene, right, and some type of acid, strong acid, like a triplet or something like that. What's going to happen in this reaction is you're going to protonate, and then it can catch it. You know, it's kind of weird because, right, it's acidic conditions, right? You're like, under acidic conditions, it would just go in the reverse. But again, if you have an excess, say, for example, of this, I'm sure there's some technical aspects behind it. But the point is, this is how you can put them on, right, and then you can take it off with PFA. What this provides you guys now is the ability to not only, say, for example, make peptides with aliphatic appendages, but one of the questions that was brought up was, well, we have amine side chains and we have carboxylic acid side chains and things like that. Just at that level, right, we would probably need a minimal of 3 different classes of protected groups, right? One class for the side chain, one class for say, for example, the N terminus, and one terminus, one for the C terminus. The C terminus. And it doesn't matter which ones you choose, but sometimes some are commercially available and others aren't. But the idea here would be as followed, right? And if we have time, maybe I'll throw up a synthesis. I'll put up an example, and if we have time, I'll put up a synthesis question. But so for more complex peptide synthesis, right? I've given you guys 3 classes of protecting groups. So the idea would be use one class for N terminus, use one class for C terminus, and what I mean by that is that's the side that's going to have the carboxylic acid, right? So use one to protect the amine, use one to protect the carboxylic acid, and then use the other class for side chains. Right? And the nice thing about that is that if you have, say, for example, you may want to pick something for the side chains, and the nice thing about that is if you have carboxylic acid, and say, for example, amines in that side chain, well, let's say you want to do a hydrogenation at the end to remove all the protected groups. So you can put, say, for example, a benzyl group on, say, for example, if you have a glutamic acid, you can put that on the side chain of that, and you can put a CBC group on the amines, and you can protect them all at the same time at the very end. Okay? So let's ask ourselves, I'm just going to throw a tripeptide up here. And we'll sort of think about how we can make it from starting amino acids, okay?
What was the acid sensitive carboxylic acid?
A T-butyl group. It's the same idea. T-butyl. So we try to stay. So for the acid sensitive, right? You can use the T-butyl group, and it's going to be the Bach group, which is also T-butyl. So there's that parallel there. For the hydrogenation, they're both sort of benzyl groups, so CH2 phenyl. The only one where there's a difference was the FMOC one, which was that complicated looking like one for the amines. And then again, you guys know just hydrolysis under, like with methanol or whatever, you could do that with like sodium hydroxide. And again, this is just sort of a mental exercise in terms of thinking about these different groups. So 1, 2. I'm going to let you guys come up with the side chains here. So here's a tripeptide. Maybe I'll just start there. Phenylalanine there. And here we'll put a protecting group, something that's going to need another side chain. So let's maybe put lysine, whatever. For border space, I'll put ornithine. Okay, and the question here, and I'm going to choose ornithine for a reason, and we'll discuss how to actually make this unit, right? And how we might make it. But we want to ask ourselves the question, how do we make this starting from the amino acid building blocks, right? And so what are the amino acid building blocks that we're talking about? It's going to be leucine, right? Or valine, excuse me. We've got valine, we've got ornithine. Again, you're not responsible for knowing these names. I should point out that when we're doing this, it's not necessarily the case. Again, I sort of gave you guys one basic strategy here, but it doesn't necessarily mean that it's going to be the most effective way depending upon what you're doing. But that's just one strategy to sort of think about that. But certainly there could be other methods as well. Okay? But certainly as we're sort of looking at this, we can build a molecule from sort of left to right or right to left. Doesn't really matter which way that we go from, but oftentimes what people generally like to do is do the amide couplings from the free amines for whatever reason. That's kind of where synthetic chemistry has sort of started, in part because I think it's oftentimes easier to put on or remove the groups from the amines and the carboxylic acids. So we'll discuss next week like solid supported synthesis and stuff like that, but for this week, let's just start building from this side forward, okay? Doesn't really matter, I guess. What did I do wrong?
How about
I did something. No, it's fine. That's fine.
all you have to do is put 48 and all the
It doesn't really matter. I mean, the point is that these are building blocks. That's not, whatever. All right, so this is fine. I don't know what I was thinking. This is fine. So again, how are we going to go about synthesizing these? So let's just start. We just got to make an amide bond. Let's just start with picking an amide bond and making it. And again, at the time that we have, let's just say, it doesn't really matter. Let's just start with those two. Let's make that amide coupling bond, okay? So the first thing that we're going to have to do is we're going to have to prepare the molecules. Again, if we can simply take these two and mix them together with ECC, that would be easy, right? But we have a lot of problems associated with them. With this molecule here, right, we're trying to make this bond, so we want to have this nitrogen protected, right? And we want to have this nitrogen protected in a way where when we deprotect this OH, right, it's not going to deprotect this. So we want to have a certain amount. So when we decide what we're going to put on here, and when we decide what we're going to put on here, right, we have to decide upon what's going to be deprotected. The other thing is that we have this group here, okay? And so we need to deprotect this molecule without deprotecting this and without deprotecting this. Now here's something that's nice, right? I sort of laid out that strategy before, which is certainly one of the things you can do specifically if you're making, more and more molecules. But this is sort of where we're starting, right? We're going to effectively lock at this point, and then we're going to grow out. So one of the last things that we're going to do is we're going to deprotect this amine, right? So we're going to deprotect this amine at the end, and we're going to keep it on there through the whole sequence. We'd also do, we could do the same thing with this amine as well. So even though I said you could choose it, that could be a strategy. In this case, we may be able to actually, now that I'm thinking about it, we might just be able to make these two the same protecting group. Make sense?
Yeah, I like that end, but not the other one.
Well, that's what we'll discuss.
That's
That's perfect, yeah. So how are you going to protect this over this? And that's what we will discuss. Okay, so this one's the easy one, right? So somebody give me a group. Right, we'll start with protecting valine. Let's put something on the valine. Yeah, I'm just going to show them in a neutral form because I'm sick of writing charges. So, so if we want to protect this as something, just pick something. It doesn't really matter. FMOC, okay? And for the time, I'll just say FMOC fluoride. So we'll protect this with FMOC fluoride, okay? And now we have to protect this group and somehow leave this group free, okay? Yeah, I mean, I think that, let's discuss this in a second. Hold on, so H2N, I'm just going to show it neutral again just because I'm... Again, I don't know, so the question is, how are we going to protect this over this? Yeah.
I think maybe people are control rate, more rate, and actually
Yeah, well, Shio, right? So Shio's saying that to think about size and bulk. We haven't really discussed different.
We did like the ruthenium thesis, the hypothesis.
I know.
Question on the test, and that question referred to this the part where the ruthenium was adding on was the part that was furthest away on the
Yes.
longest chain.
Yes. Yes. So the point here is this nitrogen here is adjacent to a primary carbon. This amine here is next to a secondary carbon. So you could make the argument that you could envision this being more accessible to react than this one based upon a steric argument. And I would agree with you. And I would say that you can actually take it to the next extent, right? Because you're saying I want a bulky group, right? So if we say that we want to do the FMOC, I'm going to show you guys something cool that basically Shio maybe could have come up with. Well, so let's say he was only getting 4-to-1 ratio and he wanted it to go all the way to 100%. And he said, well, how am I going to make this bulkier of an electrophile? And one of the ways that we've done this, and I might have shown you guys this with PBS. Did I show you guys how to select silation chemistry? One of the ways that you can do you can select for silation. No, so you can activate electrophiles using Lewis bases. So let me show you guys, this is kind of neat. So this is done, I think it should be able to be done with this. I'm not exactly sure, but I'm just going to draw, I'll just put a big thing over there for aromatic, just so I don't have to draw that group. But the idea here is that if you activate this, right, so this might react with these, and it might react at a certain rate. But if you treat it with a Lewis base, you can actually do what's called Lewis basic activation. We've seen this, I thought I showed it to you guys with the same principle. You can use this molecule. Did I show you guys this? DMAP. Did I show you guys this? So DMAP will react faster with this than this will. And furthermore, the complex that's generated then is even more activated. But the product that's generated is now bulkier, right? And so there are tricks that you can do, such as Lewis basic activation, that will allow for selective protonation. But again, you don't need to say this, but I'm just sort of emphasizing that sometimes what people will do in synthetic chemistry, if say for example, that's your hypothesis, but you get 4 to 1 ratio and you want, say, even greater, you can do little tricks like this. So anyways, you don't have to use DMAP, but that was just to sort of make a point there. Okay? So this is certainly something that you can argue would be selective, even without the DMAP. Yes?
So how would you make it more bulkier? Wouldn't it still be more accessible to get the component farther away? Wouldn't it make that more bulkier?
It's not that it's far away, it's the proximity. It's that this is closer to a primary carbon, and this is a secondary carbon.
So what does it make the primary amines more bulky instead of making?
No, it's sort of like, the good analogy would be, say for example, using a bulky base to do deprotonation of the more accessible proton, right? If the reagent that's reacting is more bulky, then it just amplifies the selectivity. So it makes this even worse, right? This will still be perhaps maybe worse, but this is a faster electrophile. This is better. So it is actually more reactive, but there will be a steric component which would make it more selective. Anyways, that was just to basically piggyback on, because you said make it more bulky, and we didn't really have a way to make it bulky. I was just saying use a steric argument, but you could make it bulky, so I wanted to just make this point. Okay, so now we have this group that's FMOC protected. We're almost out of time. And again, we could say, for example, now protect this with diazomethane or something. Wait, no, because that would be base sensitive.
Yeah.
So we want something acid sensitive. Maybe put the Bach group on there or something. Anyways, I think we're out of time. So what I'm going to say is I want you guys to finish the synthesis. So we'll complete this synthesis. We'll complete this synthesis on Wednesday. This will be good practice, so there will be something that will be similar to this on the quiz. And then the other thing that we're going to do next week is we're going to start to discuss peptide synthesis within macromolecules. So again, we're going to go off the book and we're going to discuss something called native chemical ligation, which is what the Friedman lectures, well, he was involved in doing this. I don't think that that's necessarily what he's going to be talking about at the Friedman lecture, but at least it'll put it into context for you guys. So anyway, that's it, yeah.